Okay, hi everyone. So this is just a quick video on how to initiate the assignment for ENG6A5. So if we look at the assignment, you'll see that there's a step 1 and a step 2. So we'll initiate first with step 1. So by now you would have calculated the Reynolds number, but the assignment has everything that's provided. It gives you the dimensions of the fan setup, but first of all it says to conduct a 2D numerical simulation of a NACA12 against experimental results obtained in a wind tunnel. So this is like a validation case. So we have some information here which provides us the lift and drag values on the NACA aerofoil, which was conducted here at Wrexham University. So the velocity was 30 meters per second. And the aerofoil was subjected to various angles of attack, and then the lift and drag was measured. So the first thing that we need to do is obviously first of all create an Excel sheet where we can populate our results. So looking at an Excel sheet, something very similar to this. So you can see here we've got the area, which is the chord times the span. We've got the density, we've got the velocity that's inputted in here, and then using the equation for CL and CD, we can take the lift experimental values and the drag experimental values, and we can calculate the coefficient of lift and coefficient of drag using these equations by populating the equation in here and then dragging them all the way down. It will give us our CL values for experimental and coefficient of drag values for experimental. Now, because we're conducting a 2D simulation, we obtain our lift and drag values from ANSYS simulation. As you can see here, I've done it for a fair few angles, and then we've times these lift and drag values by the depth of 0.45 to give us the lift and drag values with the depth, and then using the same equation here we can see that we can get CL and CD for the experiment, for the numerical simulation. And as you can see here, the coefficient of drag matches nice, and as you can see here, the coefficient of lift also follows the same trend and different correlation. Now, depending on your simulation setup, you can do a mesh dependency study or a turbulence dependency study, which I will show you later on how to do this in order to make it a bit more closer to experimental values, or you can investigate and see, what variation happens subject to a variety of mesh or a variety of turbulence models. So first things first is to obviously make sure you get this Excel sheet done first, and then what we can do is we can start going on to the ANSYS side of things. So before we go to ANSYS, what we need to do is we need to get a NACA profile. So closing everything down, if you go into Google, just type in airfoil tools, and in airfoil tools, click on this, go to the NACA 4-digit airfoil, type in 0012, and what you'll find is the NACA airfoil here as well. Now, some may wish to conduct a parametric study where you bring in different kinds of NACA profiles, because here this is a symmetrical aerofoil, which is your benchmark model. Some may want to bring in different kinds of cambered aerofoils for fan design. So once you've got your NACA aerofoil, what we want to do is we want to create another Excel sheet, and the Excel sheet has to be done in a specific way. So the Excel sheet here, as you can see, you've got hashtag NACA12, group, point, X chord, Y chord, and Z chord. And as you can see, it starts off with 00. And as you can see here, this is group 1, which is the upper surface. Number of points is 1 to 67. And as you can see, it starts off with 00 and then goes down to 100. And then the bottom line is group 2, and again point 1 starts off with 00 and ends in 100. So in order to do this, you go to your NACA airfoil, and there's two different types of files that you can get. here. So if you click on this one here, you can see it starts off with 0, 0, which is something that we want. So we can just simply copy all of this, copy, and then go to your Excel. So I'll start a new sheet here. As you can see, the first thing you want to do is it's going to be in C3. So C3, Control V, paste it in there. But what you will find is it's in one column, which is no good. So if you go to Data, Text Column, Delimitate, Next, with a space, Next, Finish, and then you can just move this one over a little bit, and then grab all of these, and then bring that back to C3. So we've got our X chord. So in here, very similar, you have to, on C1, you have to type in hashtag NACA12. So hashtag NACA0012. Then you got to put group, and it's very important that you put in the hashtags for these as well. So hashtag group, hashtag point, X chord underscore chord, Y chord, chord, and then Z chord. So we've got these, and then obviously here 1, 2, and then you can drag these down to where it goes to 1. And what we want to do is we want to change this one to 1, 0 there. As you can see that this has moved a little bit, so let's just drag these and put them up here. And again here, this is going to be 1, 2, and then down here. And we're going to change this one to 0, because we want to start with 0 and end in 0. So here is going to be our Z chord plus 0, and you can just double click on this little box here and it'll fill in everything until then. Okay, so we've got all of those. Might as well just make them nice and central. We've got group 1, which is the upper surface, and group 2, which is the lower surface. Now what you have to do here now is obviously save this as a save as, and you will create your own working directory. So it's very important to have everything in one place. So, you know, call it NACA coordinate or whatever you wish to want to call it, which is absolutely fine. Press save, yeah. And then to create the actual data points for ANSYS, you go File, Save As, Browse, and it's very important that you go to Text tab delimited, this one here. And what this will do is it will create you a text file. Press OK. And what you will find is in your folder it creates a text file like this, which ANSYS can read and create data points. So you've created your Excel file, you create your NACA data points. So what we want to do now is open up ANSYS. So you can just close this one down, close this one down, close this as well, close the thing, and then from ANSYS, doesn't matter which version, we will have the latest version soon in the university, so go all the way down to ANSYS Workbench. Give it a few seconds to load up. So first things first, we want to go File, Save As. Always save your work on your USB drive, or you can put it onto the C drive on the university computers, for example on the desktop, and then once you finish you can just take that whole folder and put it onto your USB key for later use. I wouldn't save anything on the desktop or on your personal drive in the university, or even OneDrive. The Ansys software likes to work directly from the hard drive, and then later on, as I said, you can just copy the folder and do what you need to do. So I will put it into my working directory. This is Briefs 2023 undergrad 6A5. I'll just call this one 2D simulation. And just to show you what happens is, in Ansys, in that working directory, it creates an icon and then a folder. Very important, you don't mess around with the folder, but once you're copying stuff from your desktop, make sure that you grab both elements. Do not put this icon into the folder, they have to be separated. So when you double click on this, it will look for the folder and extract all the information that's needed. So in here, obviously because we're going to be running a Fluent simulation, we double click and then just name this one NACA 0012. And here what we want to do is we want to create a geometry. So new DesignModeler. Now the wind tunnel dimension is 1000 millimeters by 450 millimeters, so we just need to remember that. So in the NACA 12, what we're going to do first of all is change the units to millimeters. Right click, look at, so we know what we can see and what we're working with. Now we're going to go to concept 3D curve, and we're going to go to coordinate file, and we're going to select our coordinate file, and it'll be in your working directory. So for me it's in this PC, Glindor files, module assessment brief, undergrad 6A5, and in there you can see it's got that NACA 12 coordinate. Press OK and then press generate. Now what that's done is created an upper line and a lower line. So let me just zoom out a little bit. You can see here you've got the upper and you've got the lower, and because we've done 0, 0, it's 0, 0 here for the upper, ending in 0, 0, so it's connected together. So concept, surface from edges, select the upper, lower, apply, and I did that by pressing Control to select the upper and the lower at the same time. So Control allows you to select those. Press generate and you'll have a surface in here. Now currently at the moment, for the chord length on this is basically 1 millimeter, because the coordinate files is non-dimensional, so we have to scale this up to the scale of our NACA profile, which is 152.4 millimeters. So let's double check that one. So you can see here the chord length is 0.1524 meters, so 152.4 millimeters. So before we do that, I always like to centralize my aerofoil because we're going to be rotating it from the center. So create, body, translate this surface, double click on that in the X minus 0.5 millimeters, press generate. And as you can see here, we've got 2 lines and we've got a surface body. We don't need these 2 lines again, so by pressing Control, select both of those, right click, and then just suppress the body. Now we have this, so what we're going to do now is we're going to scale this up to 152.4 millimeters, press generate, and it'll be the right size of our NACA profile. Now also we want to do is we want to make the angle to be able to rotate. So by clicking on the ZX, what that does is it gives me this, or I can just click on the double XY. It's fine, because what we'll do is we'll use the coordinates. So create, body, transformation, rotate, select the body, apply, double click on the selection, Z equals -1, and then it will have positive angles. So in here now, what we want to do is we want to put, like, you know, we can put like 10 degrees, maximum of 20 degrees, you know, any angle stack you want, but we're going to put it on 0. But what we're going to do is we're going to make it into a parametric function, because there's no point modeling every single angle when we can have it as a parameter. So click on this little box here, and what that will do is it'll pop up a little thing here, and in here what we're going to put is AOA, angle of attack, and that becomes our parameter. So press generate, and that will go green. Now what we're going to do is we're going to build our wind tunnel around this, and as I said, the wind tunnel is 1000 millimeters by 450 millimeters. So XY plane, look at, draw a sketch, go to the sketching tool here, just draw any kind of rectangle, doesn't really matter, around the aerofoil. And what we're going to do is we're going to put some constraints in and make it symmetrical. So by selecting the y-axis and then the left and the right, that'll make it symmetrical. Right click, select new axis, select the x-axis, upper edge, lower edge, and that's nice and symmetrical now. So let's give it some dimensions. So we know this is 1000 and this one is 450 mil. So now we've got our wind tunnel, and what we're going to do is we're going to create this into a surface. So concept, surface from sketches, sketch 1, apply. We're going to add this as frozen. Now, adding it as material and adding it as frozen, the difference is if you add it as material, the aerofoil will disappear because it will join the materials together. By having it as frozen, it means we can actually have them as separate entities in order to actually conduct some Boolean functions and any other kind of function that we need. So by pressing generate, you'll see we've got 2 here. And what we will then want to do is we want to create Boolean and we want to subtract. So subtract target body is our wind tunnel, tool body is our aerofoil, and we press generate, and what happens here is the aerofoil is then subtracted from the wind tunnel. So what does that mean? It means anywhere where there's grey, there is air flowing, and because there's a void in the middle, the air has to go around the aerofoil contour, and this is what will give us our simulation and results. So what we're going to do now is we just want to call this one a fluid, and it's up to you. I always like to call it wind tunnel, just to give it a name. Press generate, and what that will do is, you know, our actual model is ready in order to move to the next stage. So by file, close DesignModeler. Always best to press save as we go along, so just for good luck. And you'll see that there's a parameter set open up on the bottom here. So double click on the mesh, and this is where you can do a mesh dependency study if you wished. I'll show you some key features here where you can adjust and do things. Now, parametric study doesn't work with mesh. So if you're going to be doing a mesh study, you would need to duplicate the models in order to actually get your mesh results. So in here, first things first, as it's very simple, we can see what's happening. We can use the edge selection tool, select that edge, press M on the keyboard, and then just type in inlet on back one, N on the keyboard, outlet. Select the top surface, press Control, select the bottom surface. If you don't want to press N, you can always right click on it and create name selection here. It does the same thing. So this is a wall. And then our aerofoil again here. So there is another function, you know, if you've got multiple edges, you can either come up to this section here and select box select, and that will select it here, or you can go single select where it grabs it individually. So switching between single select and box select, there is a way of doing it on the mouse itself. So holding down the right button on the mouse and keeping it held down, if you then left click, it switches between single select and box select. So it's just a nice way of making sure you can switch through. So this is a NACA 0012, apply. And now what we're going to do is we're going to put some mesh in here. So mesh, insert method, and what we're going to do is we're going to use triangular mesh, so it's nice and quick. And what we're going to do here is we're going to add some edge selection, so selecting this and then right click on mesh, insert sizing. As you can see, everything here is still in meters, so just go to home, units, oh no, it's in millimeters. And here what we're going to do is just put a value of 1 for now, and you can see by zooming in the kind of elements that we're getting. And then on the mesh here, what we want to do is go to sizing, and we can see that it's asking us to capture curvature. We want to say no. And here, by bringing in this circle, you can see that circle represents 54.829 millimeters. So what we want to do is change that to say 10, and you can see it goes much smaller. Change it to 20, it becomes a lot bigger. So leave it at 20 for now, and then just press generate mesh. And you can see it's something like this, and we can change that to say 15. Generate mesh, and you can see something like this. So what do all these mean? So if you go down to quality, and then if you look at your mesh matrix, and as I said, the aspect ratio, you can see here it's very good. It's under 3, it's supposed to be under 10, and then obviously you've got your what's it called, skewness. So again, 0.48, very good. So it needs to be under 0.9. And in the statistics here below, you've got the number of elements. So this is at the moment 7,948 elements. So doing a mesh dependency study, you can look at the aspect ratio, you look at the skewness, but fundamentally you look at the number of elements. So the more elements it has, does it give you a definite difference in the actual results or not? So I'm going to stick with this mesh just for this purpose of this tutorial. So on the wind tunnel, I'm also going to create a name selection called air because it's fluid. And then here we're going to then make sure, so if you click on mesh here and click on mesh there and press update, what it will do is it will update the mesh a lot quicker. So there are other ways, which is basically just closing the mesh, and then you can just right click, save, yeah. Oh, sorry, by accident I've closed it down, so double click on 2D Sim. So again, this is another reason why you should always save your work as you go along. Sometimes you can accidentally close. Okay, so it should load up. Yep, so you can always right click and press update on here, but it's a lot quicker by doing it within the mesh function. Having the mesh opened up and doing it that way is really good. So now what we're going to do is, we've done the geometry, done the mesh. Now in the assignment, I do require, how did you create your model and mesh? So there needs to be some form of a descriptive information in your assignment on how you did these kind of functions. So so try and remember the whole process and be quite specific. So in order for it to be replicated, so somebody else reading your assignment can see what you've done, how you've done it, for them to actually replicate. So double click on setup, and in setup here, so if you're using the university computers, you can use quite a few processors. So we've got 8. If you're using your home student version of the software, the maximum you can go is up to 4 because they've constrained it, so you can only use 4 logical processors. So for this purpose, I'll just use 8 for those that are using it on the university. So press start. What that means is basically the model will be split into 8 different segments, and each core will run the simulation for that segment, which basically just speeds up the whole process. So it should open up with answers, and then just press OK on this, and what you'll see is you've got the velocity inlet, velocity outlet, and you've got the Naka airfoil in here. So first things first, turn on gravity, minus 9.81, and in the models you can see that the standard model is the viscous SSTK omega, and here is somewhere where you can do a model dependency study. So you can turn on the SPA almas, you can do the K epsilon, or you can do the K omega, and you can change these three and see which one, is there a difference in the results for these three turbulence models. So that's something else that you can variate, and it's something that's, gets you extra marks, should we say. So we'll leave it on the standard model that it comes with, and then obviously here we've got the material properties, air, and you can see here it's 1.225, 1.7894 as your viscosity, and in the assignment you can see it uses 1.789. This won't make a huge difference. This was obviously measured in the experiment, but it won't make a huge difference in the actual results of everything. So I forgot to actually put density in here, so the density will be provided in your assessment brief. So 1.225, change and create, close, and then obviously here what we want to do is we want to go to the boundary conditions, and in the inlet, sorry, I do apologize, the density is not provided in here is because you will have to calculate the density. So I provided the equation down here somewhere. So density equals the pressure divided by RT, and the pressure again is all provided. So you will have your own density value and your viscosity value. So you might actually want to go into, as I said, remember CFD is only good as what it is to experimentation. So you might want to change the density and the viscosity according to the experiment. Okay, so important to change those things. So close. Now obviously here we go into our boundary conditions, we go into our inlet, and in the inlet here we put in a velocity of 30 meters per second. And what we can do is we can change the hydraulic diameter, because we know what the diameter or the wetted area here is, which is 0.45, which is 450 millimeters by 450 millimeters. So press apply, close, and then what we done to the inlet, we should always do to the outlet. So in here again, hydraulic diameter 0.45, press apply, close. So we've done the inlet, we've done the outlet. We can now go into initialization, and we're going to use the standard initialization, compute from inlet, initialize, and then what we want to do is run the calculation. Now give it 1,000, and it should do within 1,000. So I'll quickly just check it here now. So as you can see, it's already finished and it's converged by only doing 55 calculations. So what we can do now is obviously we can look at some contour images, we can look at some path lines. So here, it's not asking for a lot of information, but the main thing it's asking for is the coefficient of lift and coefficient of drag. But it's always nice to put some images into your report. So if you go into your graphics, contours, here we can press the pressure and press display, and you can see what the static pressure looks like. Now you can zoom in, you can zoom out. So static pressure is very good, and also the velocity magnitude is also very good in order to see what's happening, to the actual results. Now, the best way to, find a view that you quite like, that you'll be using for all of your angles, because there's no point showing all the angles for the simulation. So it's always best to show maybe a max of 4 angles in order to see what's happening. So for example, let's just say we'll do it for velocity magnitude. So by going into your view, you can actually save this view, so you always get the correct view for all the other angles. So you can just name this one and call it CFD post, save. You can then just to be on the safe side, write this one, CFT post, and again, put it into your folder. So assignment support is my working directory, and call this one CFT post view. So you can always load it up for various models if you wish. So press close. And the best way to take this now is right click, copy to clipboard. And then what I'll do is I'll open up, I'll just use this one. Let's go down here. And I can just, paste it here, and you'll see, it gives you a really nice high quality image in terms of what you want. So there is some other you can take also is the XY plot. So XY plot, X equals 1, pressure, static pressure of the NACA aerofoil, save and plot. And this provides you the pressure distribution of the NACA aerofoil. So you can again here go to curves, pattern, line, apply, get rid of any symbols, save and plot. So it plots the NACA profile like this. And you can order the points and write to file, and again right here. So 6A5, and this is AOA 0D, so the 0 degree of angle. And what that does now is I can actually go to my folder, open up Excel, any Excel, just leave that one open, and then basically this, where did I call it? 0, I need to put that in there. If I drag and drop this one in any Excel and press yes, it will create my data points. So I can actually now use this, insert, and it creates me a data point there. So you can see here, it's showing me the chord length and the pressure distribution that's happening. So we'll leave that there for the moment, because what you can do is you can bring your other 4 angles into the same one, and then you can show that this is for 0 degrees, the other one is for 4 degrees or 10 degrees or whatever you wish. So we also need to get our lift and drag values. So what we're going to do is we're going to create a parameter. So we've got images, we've got static pressures, and what we're going to do is we're going to go into reports, surface intervals, okay, sorry, not surface intervals, forces, okay, and before we do this, we must go into the reference values, not reference values, reference values. We compute from inlet, okay, the length is 0.1524, the depth is 1, and the area here is going to be the same area, which is your chord times your length, which is this value here. Okay, that sets the results to calculate our lift and drag values now. So you can see here, if I go to forces and I press for x equals NACA 12 print, this will give me my drag value, because when x equals 1, it's drag, so 0.0436, and when x equals 0 and y equals 1, it gives me my lift value. Okay, so what we want is we want those to be as a parametric function. So if I go back to x equals 1, put a 0, and I save output, and I call this one drag, and then x equals 0, y equals 1, and this is lift, press OK, close. I'm just going to go into initialization, compute, inlet, initialize. Okay, so the simulation is now ready to do a parametric study. So file, close Fluent. And then I can go back to my Workbench, and in my parameter set here, I can say, okay, so what angles do I want? So I don't know, for the moment here, I'll do 0, 8, 16, and 20. But I want to retain them, because if I don't retain them, it means that I can't go in and get images and pictures, because the only one that's retained is my 0 degrees. So I want to retain all of these so I can go inside and get my pictures, get my results that I need. So if I just press update all design point now, what it will do is it will run the simulations in the background and just give me my drag and lift values. So give it a few seconds. I'm just going to press pause and return back. Okay, so as you can see here, it's all complete and finished now. So I've got my 0, 8, 16, 20, and I've got green ticks. So it means I can go back to any one of these simulations and have a look at my results. So as you can see here, we've got, you know, the drag values and lift values. So what I'm going to do is I'm going to put those in for these angles. So for lift, it's minus 0.685. For drag, it's 1.651. And then for 8 degrees, it's lift is 62.95, sorry, 62.07, and for drag, it's 2.73. And then you can see here for 16 degrees, 61.95, 15.1. And then for 20 degrees, we've got 65.52, and then you've got 23.8. So you can see that, you know, it's not bad. It's, you know, it's following the trend. The one good thing about it is that there is a stalling angle taking place, you know. So, but here you can get it a lot more closer by maybe looking at the turbulence model, maybe looking at the mesh, to see, you know, what effect it has. And if you are doing a mesh dependency or a turbulence dependency study, I wouldn't do it for all the angles. I would just do it for the 4. But fundamentally, once you get your best results for the one that's the best turbulence model, the best mesh, I would then basically do all the angles for that model in order to show the final results of CL and CD with all the angles and your CFD results. And that's the one that I would put also in the end conclusion of your 2D simulation in your assignment. So how do we go back? At the moment here, you can see that DP0 is the current parameter. So just say, for example, I'm going to go to the 20, right click on that, and then set as current. It means now the 20 degrees is the current one. So if I go back to the project and click on solution, do not click on setup, make sure you click on solution, and in there you will now, it will open up the 20 degree results. So again here, what we can do is, you know, go to the graphic contours and press display for velocity. But you can see the views changed. So you can go to your views, and you've got that CFD post, press apply, and you can see that that's the same view now. So now when I right click, copy to clipboard, and then I go back to this one here, I can paste, and you'll see that it's the same exact location and view, which is really nice and smart. Sometimes it's very hard that some are zoomed in, some are not zoomed in. So that's just one way of just making sure your results are nice. And again, we can go to XY plot, and in here, you know, you can take these images as well. So you can, you know, you can plot these ones. You can again, you can just take, you know, copy to clipboard. But if you want to get extra marks, you know, you order the points, write a file, write. And again here, just make sure it's in the correct place. So angle of attack, 20D, okay. And then if I go back to Excel, I can then drag and drop that 20 in here, press yes. It'll open up another Excel sheet, and you can just copy this one, copy, and then go back to the one that you were there before, and you can paste it next to this one. And what you can then do is grab your actual graph. Let me just go select data. Select data, we can add another one, X value. There's a way of pressing Control Shift and an arrow, it will just grab those. And then Y, again, going to the top, pressing Control Shift, arrow, down, press OK there, and hopefully fingers crossed. So sometimes it does this kind of approach, which is a bit of a weird thing that it does this. As you can see, the numbers are kind of like funny a little bit. So I would go back to ANSYS and maybe in the XY plot, not order the points, just write to file. Undergrad, 65, 20. Bring that one back in. Yes. And as you can see here, it hasn't done it this time. It's put it in the correct format that it should be. So we just grab all of these, Control C, come up here, and I could just Control V there. There we go. There's a few points that it's a bit mistaked, but you can fix those very simply just by finding them and making sure. So sometimes it does this, but as I said, you can either do it this way or you can do it by taking in the graph and putting it in. There are other methods of doing these, which is basically in ANSYS. So in ANSYS itself, you can actually go to the XY plot, profile data, and you can actually, hold on, where is it? Close plots. Load, add XY plot, or load files. And in here you can actually go to your support, go to all files, select your 0 and 20, press OK, and then plot these. And what it does is it plots to both at the same time. And then again here you can go into your curves. And because curve 0 is the black one, is your NACA 12 at 0. Again here, apply. Here, apply, close, plot. Weird, it does that. So again, go to curves, maybe just go back to 0, apply, close, curves. So you can plot it like this, and then you can take an image of this one here, and you can change the names of these as well. So again here you can name this one to say AOA 0, and then here AOA 20, and you can see the name changes there as well. So you can change those that way. So again, that's just another way of presenting here. But for the NACA 12, it's up to you what you show, and this basically shows the distribution of the pressure at 0 degrees. This one here, you can see that the upper and lower are exactly the same, being a symmetrical aerofoil, but as the angles of attack are increased, the pressure distribution changes around the aerofoil. So that's part one, should we say, of the assignment. If there are any questions regarding this, you can always ask me, but specifically what we want for this is this Excel graph here. This one here is the most important one, which basically, as you can see in the assignment, it stipulates here. So we've done the Reynolds number, we've generated the 2D numerical model, making sure that the mesh, boundary condition, and the solver are adequate and determined for terminus modeling. Conduct CFD simulation by applying oncoming velocity inlet boundary condition based on the experimental data and present simulation results of the flow over the aerofoil at various angles of attack. So again, here are some images of static pressure or velocity magnitude. Again, not too many, but up to you what you want to show here. And again, as I said, no point showing every single angle. Pick, 0 and 20 is definitely a must, and there may be one or two more in the middle, which are really good. But question D here is to determine the CL and CD profile of the aerofoil using the function reports, which is what we've done, and then obviously we've compared the CL and CD against experimental data. So what that does is this tells you that your validation is done, your simulation model is correct, and depending on the mesh and the turbulence model that you've used here, you will use that same approach to move on to step 2, which is going to be conducting the 3D analysis using the actual NACA aerofoil. So once we go into this, what I'm going to do is, we'll use the same ANSYS workbench. It's always best to have everything in one place. You can have different ones, if you wish. If you want to have one for your 2D simulation workbench file and then close that one down and then open up a brand new workbench file for your 3D simulations, it's completely up to you. But for the purpose of this, I'm just going to use the same workbench file. So again here, what I'm going to do is I'm going to use a new Fluent. I'm going to go into new DesignModeler. Give it a few seconds. Okay, so make sure my units are in millimeters, and we've got everything in here. So again, the first thing to do in here is, if you look at the assignment, it gives you the dimensions of everything. So we've got a hub, which is obviously centrally in the middle, and it's very important that our rotation center is actually in the middle. And we've got, the overall diameter is 30 for the hub, 60 for the overall fan, and 64 for our working domain. We've got a width of 12, and in the front of the fan we've got a 10 area, and then overall is 80. So first things first is always best to just, use, get our fan blade at first, and you can see it's got an installation angle of 25 degrees. So what we're going to do is we're going to set it up as 25 straight away. So in here, what we're going to do again, use a NACA profile. So concept, 3D curve, select our NACA coordinate, apply, generate, click on the face value so you can see, create, body, concept, surface from sketches, delete, surface from edges, apply, generate, create, body, translate, move this one, minus 0.5, generate, okay, and then what we'll do is suppress these. Not part, what have I done? Blue part, suppress body. Okay, so we've got that. Now in the assignment, it says that the actual chord thickness, the length, hub width, chord is 12 mil. So what we're going to do is just create body, scale this one, apply 12 mil, generate, and then what we're going to do is we're going to create body, rotate, apply, -1, So that's 25 degree angle. Generate. And you can see here, that's the angle that it's going to be at 25 degrees. So what we're going to do now is we're going to create our hub. So create primitive cylinder, and the cylinder, as you can see, is facing towards in the Z direction. So what we want to do is change that one to the YZ. So it's facing that way. And the radius for this one, so you can see it's 30. So the radius is going to be 15. And the thickness is 12. 15. 12. Okay, and then as you can see, it's in the Z, so -6 puts it dead smack in the middle there. Okay, so we press generate for that, and what we're going to do is we're going to view wireframe. Okay, so obviously here we can change the angle of this one. So, if you said you want to go 30 or 45, you can see that it changes the angle accordingly. So what you want to do is you want to start off with 25, and then this becomes a parametric function again, in order to see what happens with the angle changing to the actual design of the actual fan itself. So we've got our hub, we've got our blade. Now what we're going to do is, in this actual plane here, the XZ plane, we want to create a path. Okay. Now why we want to create a path and not just extrude, there is a difference. So what I'm going to do is I'm going to create a path. So I'm going to insert a sketch, and then I'm going to sketch a line. Sketch. Base sketch. Okay, right. What's happened here? Cancel. Delete. Okay, sketch 2, and in that sketching, what we're going to do is create a line from the center. So you might want to zoom in and get a P, and then just come out vertically on this line here. And what we're going to do is we're going to give this a dimension. Now it says 30. Now if you remember, the overall diameter of this is 60. So what we want to do is we want to go a little bit more. So an extra 10 mil should be absolutely fine. So press generate. So now what I can do is I can actually sweep this surface body, apply along this path, and press generate. So what that will do, and I need to add it in as frozen. As you can see here, what's happened, because I've added it in as material, it's united it. So I'm going to add it in as frozen, generate, and there you go. So I've got one of my blades. Now why I created a path like this is because if you wanted, you can actually put in, a twist or a pitch into it. So for example, this one's got, say 400. You can put in a pitch into it, so to create kind of a different thing to it. So 400, will that work? Yeah, so you can put different kinds of like twists and pitch to it, but here for this purpose we put no twist. Okay, so we got that. Now what we're going to do is we're going to use the pattern function and apply circular, and the number of blade is fixed. It's always going to be 6. Okay, so we want an axis, and the axis is going to be the Z axis. So click one of these, and you've got apply, and we want 5, generate. So it's created our 6 blades. Now what we want to do is we want to trim these. Okay, so first of all, we can unite these together. So Boolean function, unite, press Control A, apply, generate. So it's united all of those together. And now what we can do is we can trim the outer edges of those. So create primitive cylinder, and again in the YZ apply, and we know the oval diameter is 60, Z is 30 there, that's fine, no problem, minus 15. And what we want to do here is we want to use this as a slice material, generate, and what that will do is it will slice the upper parts, which means now we can actually just select these individual parts, create, delete bodies, apply, generate. Okay, so now we've got our fan perfectly ready with our benchmark model of 25-degree angle of attack, and the blades are 6 being set, and we've got our hub. So now what we can do is we can generate our actual domain. So the domain is a cylinder as well. So again, in the YZ, add it as frozen. Now we know that this is 64, so 32 diameter. We know it's 80 in total in length, but we know it's got a 10 mil gap in the front. So this is 12, so add the 6, so it's 16. So we can go minus 16 there, and we have our domain that we need. So we've got our domain there. And now what we're going to do, because this is going to be rotating inside of here, we need to make a domain which only fits around this, which then allows the fan to rotate at a given RPM. So again, what we're going to do is we're going to just see that surface here. We don't need that to be exported, so we can right click, suppress body. We can then create another primitive cylinder, and again in the YZ, but this time we're going to add it in as a slice material. And we know that the diameter is 60, this one is 64, so we're going to give it a bit of a 2 mil clearance. So what we're going to do is we're going to put in 31. Just 1 second, let me just double check something. Uh, 64, 60, that's right, yeah. So we're going to give it 31, and we know that this is 12, so give it, you know, a gap in between, so 12, 13, 14, so 14, minus 7, so that should give us a mil in front, a couple of millimeters in front, and then as you can see here, it gives us a bit of a tip clearance as well. So generate that, and we've got a kind of zone around with a bit of a clearance, and then if you click on this one here, we can see that there's a bit of a clearance there as well. So now that we've got these 3 zones, we don't need the actual fan itself. Okay, so what we're going to do is we're going to create a Boolean. We're going to subtract, and the target body is this one, the tool body is this one. But what we're going to do is we're going to retain, preserve the body, because we need that body for the FEA analysis. So what we're going to do is, by generating this, it would subtract this from this body. But what we want to do is, this is a solid, and we're going to call this one FEA, because we'll use that later on for the FEA analysis. This here is the it's a fluid, and this is the stationary air, SA. And this is the rotating air, so it's a fluid, RA. Okay, so we've got those, we've got our bodies, everything's ready to move on. And again here, you know, how did you create this is important as well. So let me just show you in terms of the concept of what these look like. View shaded exterior, so you can see it here. So if I suppress the FEA, suppress that, you will see that there's an actual cutout of the fan, which is an empty void inside. So I just want to just show you that. So unsuppressed body, we've got that there. So what we're going to do now is go File, Close DesignModeler, and again, very important, just make sure you always save as you go along. Right, okay. And here we go, we've got the mesh now on this. Okay, so the mesh is loaded up. Now, as I said, as it's like this, it's always best to just, you know, name everything. So selecting the face and inlet. Well, we don't know if it's a velocity inlet, so what we're going to do is we're going to call it a pressure inlet. And then pressure outlet. And then this is a wall. Now to get to the fan, okay, there's a variety of ways of doing it. You can either just go to the geometry, and now we don't need the FEA model for the CFD, so we're going to suppress that straight away. So you can go to stationary air, and you can just hide that body, so you can get inside, and then selecting these here, and then just right click and hide faces, hide face. And now you can just press Control A and it will select our fan. So fan. So in the name selection now, we've got pressure inlet, pressure outlet, wall, fan. We can show this body now. And then here, as we've got that, we might as well create name selection, SA, stationary air. And we've got RA, create name selection, rotational air. Okay, so we've got all our boundary conditions done. Now obviously it's important to put a mesh in, so insert method, Control A, apply, and what we want is tetrahedrons. Now we want to make sure that the mesh on the fan is small as possible. So what we want to do is we're going to go to SA, hide this, no, we can leave it as that, it's not a problem, because what we'll do is we'll use edge tool selection, and then use box select, and what we can do is make a box just around the fan. Okay, so just geometry there, because otherwise everything's green, so you want to see what's green and what's not. So you can see it's selected the front edge as well. So again, just very smartly if you can. Yep, it's got all of the fan blades that we want. So mesh, insert sizing, and again here, start off with an element size of 1 mil. And then what we can do is select the hub, mesh, insert sizing, give a value of 2. And then we can select all of, remember there needs to be 4 edges here. There's 4 edges because there's 2 edges in the same space. So mesh, insert sizing 3. And now when you click on the mesh, you can see there's a big circle and a small circle. Now what that means is if you click on the sizing and again just turn off capture curvature, what you'll see is the bigger one is 12 mil and the inner one is 6 mil. So by changing these again, say 5, you can see that that goes to 10. So 4, and that's 8. So let's just generate mesh there. So we've got this mesh here. It may be good, may not be good. It's something that you can investigate and something that you would know from the 2D simulation. So again, looking at the quality here, You've got your aspect ratio, so 5.74, which is very good, and then you've got your skewness, so 0.9, so that could be maybe improved a little bit more, depending on this. And again, as I said, you look at your statistics as well, so 83,000, can that be made a bit more better or not, depending on your mesh study. So again, update here, it will tell you that your mesh has been transferred, so file, close meshing. So in the setup, again, being 3D, I'll use 8, start. Okay, so gravity turned on, minus 9.81, and then obviously we go into our boundary conditions. Now, obviously we know what the diameter is, so what we can do is, it may create some walls, ignore those, you've got nothing to worry about, just make sure that the pressure inlet is pressure inlet and pressure outlet is pressure outlet, and the fan is supposed to be wall, so that's fine. So you can go into here and you can change these to hydraulic diameter, because we know that it's 0.064 for the inlet and for the outlet. So the main thing now is, obviously we know the material is air by standard, so we can just make sure that the air is fluid, which is absolutely fine. And what we want to do is we're going to go to cell zone condition in the rotational air. So because it's in the X direction, if X equals +1, it will rotate, well, if X is pointing towards you, it will rotate in the anti-clockwise. When X equals -1, it will rotate in the clockwise. So we want this to rotate in the clockwise direction. So what we're going to do is we're going to do frame motion, go to units, angular velocity. I always prefer revolutions per minute rather than radians per second. When X equals -1, we put the revolutions per minute of 1,500. Apply, close. We also want to go now to the boundary condition, and we're going to say same to the fan. So the fan, again here, is a moving wall, it's absolute, it's rotational, and X equals -1, Z equals 0, and it's 1,500 RPM. Apply, close. So initialization wise, you can use the hybrid because there's something moving in here, so it might be good, but what you will find is it may say that the mesh is not convergence enough. So you can see here that one of those have done, the other one hasn't. So again here, depending on the mesh, it will do a convergence, but it's absolutely fine because what you can do is you can just run the simulation to see what's happening here. So 1,000, just calculate. And again, what you're waiting for here is for the simulation to automatically stop and say that it's converged. If it doesn't stop, like you can see here, it's kind of like plateauing, it's just going dead straight, or some of it's quite going up higher. It just means that the mesh is not adequate enough, it needs a lot more in order to actually, to fine tune the calculation. But as you can see here now, it was going up, and slowly it's coming down as you go along. So I'll just give it a few more minutes. And it may not converge. So again here, you would need to increase the mesh a little bit in order to fine tune it. So what I'm going to do is I'm just going to stop it now. Press OK, and I can go to my graphics now, and I can again go to contours, click on the fan, save and display, and I can show you what's happening with the pressure forces. Now, obviously, we want to make sure that, is this actually rotating and doing what it's supposed to do? So one of the best ways to double check that it is working is by looking at the path lines. So by selecting the path here and then skipping by 20, pressing save and display, you should be able to see that there's an actual rotation taking place. And as you can see here, there is definitely rotation taking place. So that that gives you confidence that the actual RPM fan is rotating. So again, going back to your contours, here you need to represent some images. Do you do, static pressure is one of the key ways of understanding what's actually happening here in terms of the fan. But you can also create some, some planes. So by creating a plane in the XY plane and then putting that to 0, create that. You can go to the contour and you can show your plane. What's happened here? I don't know, because I've got the plane manager opened up. Okay, so you can show what's happening here in terms of the static pressure, and also you can show velocity as well. So what's happening to the velocity in the actual system because of the vortex in here. You can see there's a big vortex taking place. So again here, what kind of images you can take. You can also take, create some more planes, not parametric, to obtain some information. So again, the plane will be in the Y, Z. XY, sorry, YZ. Yeah, so the YZ, and you can say, well, I want to create quite a multiple amount of planes. So I might say, okay, I know my 0, 0 is in the center of my fan. So I might say, okay, I'll go 6, 7, 8, 9, 10, so 10 millimeters before minus 0.01. So create one there. I can go behind 10 mil, 10, 20, 30, 40. Okay, now what that does is it creates some additional planes. So what I can do is I can turn those off and I can go with 9, 10, 11, 12, 13, and I can display what's happening here. Now, what does that mean? It means I can actually now go to surface reports, surface plane, surface intervals, and I can get the area weighted average static pressure for those. So 9, 10, 11, 12, 13, compute. And what it does is it gives me the static pressure, and I can produce a graph now by taking these values. So for example, I'll just show you quickly now. So Control C, go to, I'll just go to any Excel. Let's go here, Control B, copy, Control B. Okay, so again here, because it's in one plane, data, text column, eliminate next. Yep, next, finish. So I know that plane 9 was minus 0.01 meters. Then it was 0.01, 0.02, 0.03, 0.04. So that one comes there, and then I've got 10, 11, 12, 13, and here you can plot a graph. Insert, scatter, so you can show what's happening with the static pressure at various locations of the fan system itself. And you can do the same with velocity as well. So you can take velocity, compute, and it shows you the velocity, what's happening. So just before it's 1.04 meters per second, and then 1.76, at 11, 1.34, 1.45, and then 1.53. So the velocity increases and decreases. I mean, the simulation hasn't finished and it hasn't converged, so that's why there's a bit of a dip and a glimpse. I mean, something that you might want to do is when you create your planes, name them. So you can name them minus 10, 10, 20, 30, 40, and that way you can remember which one's which. So that's one key factor in terms of what you can present in terms of data, and by changing the actual angle of the blade, it will give you different kinds of results. Is it being better or not? But how do we know the overall performance if it's doing very well? So in the surface integrals as well, you've got basically the volumetric flow rate. Okay, now the volumetric flow rate, if you select the outlet, pressure outlet, it'll tell you how much air or volume of air is flowing through the actual system, and as you can see here, it's, minus, well, don't ignore about the minus, but it's 0.00197 meters cubed per second. So we can't change, obviously we can make that, a lot faster, a lot more air going through by, changing the RPM, changing the blade, but because the number of blades are fixed and the RPM is fixed, the angle of the blades will have an influence of how much air is flowing through. Also, the design of the blade will also have an impact on how much air is going through. So sometimes it's maybe important to save this as an output parameter, so volumetric flow rate. And also, it might be nice to know what the velocity is. So area weighted average, how much air is being extracted. So pressure outlet. And so V out, and then also V in. V in. And what that means is, you can see that by changing the design, what happens to the velocity going in and what happens to the velocity going out, okay? So, and that way you can do a parametric study in ANSYS here, with, for example, different, I haven't made the blade installation angle into a parametric function, but you can change that, by just going in there, clicking on that box, and it'll change it into a parametric function. In DesignModeler, and then you can get the volumetric flow rate out, and you can then start doing comparison study of your blade installation angle against how much volumetric flow rate is flowing through, what makes it better, what doesn't make it better, how much velocity is going in and how much velocity is coming out. Now, what I want obviously is, as you can see here, it's just done that because I've copied the parameters. Now, what I'm going to do is show you what happens next. So once you've got your best fan model, okay, I'm just going to go into the solution here, solution initialization, run calculation. I'm just going to do 100, calculate. Now, why I'm doing this is because I need a green tick to move to the FEA analysis. Okay, so, okay, file, close Fluent. And you will see that there is now in the Workbench, there should be a green tick next to the solution. So what I can do now is, I'm going to bring in a static structural analysis and put it directly on here. I can go into my engineering data and select some other materials. So for example here, engineering database, I can go into, explicit materials or hyperplastic materials, so non-linear materials. So you've got some, you want to use some kind of plastic materials. So if there's something that's not on here, you can bring in your own. So for example, I'm just going to say for the moment I'm going to use polyethylene. There is no other kind of plastic materials here anyway, so I just use polyethylene for this purpose. Go back to project, go into model. Just give it a few minutes, it's just loading up now. And this is only done on the best model towards the end, because you'll have a fan that you've optimized to be the best. And then what you want to do is you want to do a material analysis on these. Now in here, what you want is, you don't want the SA, you don't want the RA, so you suppress those. So suppress body, and all you want is the FEA. So generate just a generic mesh. It's not a problem. I mean, here, I would make it straight away a little bit more smaller. So 2. Now the mesh for FEA is completely different to the mesh for CFD. So just remember that a little bit. So sizing, capture curvature. No, okay. So that's fine. Now you can see here imported load has come on board. So insert pressure. Okay. Now select the geometry. So you want to select all the faces, apply, and the surface you want is the fan. Press enter on the keyboard. There is no apply button, just press enter by selecting the fan, and then import load. And what it will do is it will import the pressure forces calculated in ANSYS and bring it onto your FEA model as a pressure value. And then what we want to do is we want to create a fixed location. So what we want to do is, obviously, this fan itself, we want to say that the hub, is located in the middle. So we're going to put in a fixed support here and here, so it can't, move anywhere. And then here we can then look at some deformation. So total deformation. We can look at some stress, but we can also look at the error as well. Equivalent von Misses. Press solve. And what it does is just building a model and just running the simulations. And as you can see here, we've got some deformation taking place. Okay, so you've got some total deformation, you've got some structural error as well. So the structural error is no good. What that means is the mesh isn't good enough for those kind of regions. So what we want to do is we want to make sure that we apply a lot more nicer mesh. So again, using very similar approach to before. If you used the edge tool and then select your edge, as you can see here, selected this hub, you turn that one off, and we can say, okay, well look, we want some nice, more fine sizing edge on here, so 1 mil, or you can go even a lot more smaller, generate mesh. And as you can see, it's created a lot more nicer mesh elements for those. And again, if you just press solve, and as you can see now here, you get a bit more nicer kind of analysis of what's happening here. Now, obviously, this is scaled, massively. You can see that it's so true scale is this, so there is actually very, very, very small deformation taking place, being made out of plastic. But it's just your understanding of how to do a fluid structural interaction. So you can see the strain values. Where is going to be the maximum stresses? Obviously, the maximum stresses are going to be at the root where they're being joined. And then obviously, where's the maximum deformation? Obviously, it's going to be at the tips because they're the fastest moving parts of the simulation. So you can also take some nice kind of results from these as well. So what you can do is you can create path lines. So in here you can insert some paths. Insert. Okay, construction geometry. You can create some paths, and those paths in itself, you can create 2 points, or you can select an edge So, you know, the edge selection, you can say, okay, well, I'm going to pick this edge here, okay, and that becomes a path. You can also insert in another construction geometry, so path, and say, well, I'm going to do it at one of the roots, so that one there. Okay, so we've got two edges here, and then what you can do with that is you can go to the solution, and you can say, for example, stress, again, equivalent stress, but this time use the path, and the path that you want to use is obviously path 2. Path 2 here, press solve, and what you can see is you can see stress values along there, and then again here you can go to deformation, so home, results, solution, deformation, total deformation, and again here you can select your path, and then it will be path 1, solve, and it shows you the deflection along here as well. And you can extract these and put them into ANSYS, or sorry, put them into Excel, and then put them into your assignment. So, okay, so I've been going on for quite a bit now. It's been about an hour and 26. I mean, I've tried to show you as much as possible. Everything that I've done here is, you know, to initiate the assignment in order for you to get going. And as I will be in the actual lecture, you can ask me as many questions as possible, and you know, I can give you some guidance in terms of what extra you can do in terms of the simulation. Have a look at the marking scheme. It tells you very clearly how to, you know, gain extra marks, what to do, what not to do. There are ways of, you know, using the result function here, answer CFD post. It's just a little bit long-winded. But you know, you can actually, you know, use that to produce your images and graphs and stuff, which again I'm happy to show you, but not 100% necessarily needed. Now, some of you may want to use other alternative software specifically for the 3D. So you might want to use SolidWorks or Inventor, CATIA, whatever you wish, you know, to import your models in, which is absolutely fine, not a problem at all. You know, this gets you extra marks, but just remember, when it comes to parametric studies, DesignModeler gives you that function. Otherwise, you would have to duplicate all of these and have them as separate different models in order for you to do what's needed. Okay, thank you very much.